Good afternoon, HL2 students. As I said in my note on Canvas, I am sorry that I am not there with you today, but I am home with a sick family member and awaiting a call from the doctor. So I'm going to take you through. So this note sheet, you don't have it printed out, but that's okay. You can just take notes on your own sheet of paper. And actually, what we're going to be doing here is a lot of just theory. So you might even just sort of watch the video and take down a few little notes, and then I'll have it printed out for you tomorrow. This page of the notes, I'm actually going to wait and do with you tomorrow just because there's a lot there, and I would rather do it with you in person and talk to you in person. So these are the problems, though, that I want you to try tonight. Just a couple problems with answers. And I'm not doing any sample problems. I'm just talking to you about some formulas, and then I think you can just dive into the formula and use it. Okay, so let's start out first of all. So this is cross products, and this is sort of part 2, so the second part of it. And we're first going to look at the magnitude of the cross product. All right, we talked about how to find a cross product using this formula, and I showed you a shortcut for that. If you were absent on Friday and you have not watched the video from Friday, hopefully you have, so that you could turn in the homework this morning. But if for some reason you haven't, then you need to watch that video so that you can see the sort of the shortcut for how you can do a cross product. But what if we want the magnitude? All right, we know that the cross product is if I have two vectors like this, those form a plane, and the cross product is the vector that is perpendicular to that. And there are infinitely many that will work. So if this is A and this is B, then this is A cross B. It's perpendicular to both of those. So we want to know what's the magnitude of it. Well, one way we can find magnitude is just going back to the definition of magnitude, all right? We've got the component form of our cross product, and so the magnitude then would just be the square root of, and then it would be this squared, so it's kind of a mess, but it would be A sub 2, B sub 3, minus A sub 3, B sub 2, quantity squared, then plus this squared, so we would have A sub 3, B sub 1, minus A sub 1, B sub 3, that quantity squared, plus, and then we would have this quantity squared. So A sub 1, B sub 2, minus A sub 2, B sub 1, quantity squared. Okay, so that would be one way that we could find that. But there's a second formula that's going to be a little more compact and a little more convenient for many problems. And you're going to see that there's some similarity to the formula that we had for dot product, which was this one up here. So you're going to see sort of a parallel in there. Okay, so here is the formula. I'm going to give you the formula, and then I'm going to take you through this proof that we have right here. So the second formula says that the magnitude of A cross B is going to be the magnitude of A times the magnitude of B times the sine of theta. All right, where theta is the angle that's between the two vectors. And if you go back to the dot product, remember this is the formula that we kind of emphasized because this is the one that helps you find the angle between two vectors. That the cosine of theta is the dot product divided by the product of the magnitudes over here on this side. And if I multiply both sides by this, then I end up with this by itself, all right, over here, and I flipped it to the other side, times, and then this times this. So that's where we get this. So you can see some similarity. Now, notice that this, of course, is not the magnitude of the dot product, because that doesn't make any sense. The dot product already is a number. And then this will just be a number, because this is magnitude, that's magnitude. Those are both just numbers. Cosine of theta is just a number. But over here, what we have is you see the magnitude of A, magnitude of B, so that's similar to what we have here. Instead of cosine of theta, it's the sine of theta. And then it is the magnitude, because remember that the cross product gives you a vector. And so because these are all numbers, to make this a number, we take the magnitude instead. So here is the proof. I'm not sure why this keeps freezing. All right, so here's the proof. So we're kind of going to do this backwards in a way. So what we're going to do is we're going to start with this side, and not just start with this side, but start with this side squared. And you'll see in a minute why we need to do that. And so if we're trying to prove that this equals this, but we square this side, then we're going to start out proving that this is equal to this squared. And then we'll just take the square root of both sides. So follow with me along with the proof. Actually, there's sort of a big chunk that we leave out in the middle just because it's really messy algebra. But the rest of it you should be able to follow, and I think it's a good review of some trig. Okay, so like I said, we're going to start with this side squared. And we want to prove that it's equal to this squared. So this side squared is going to be the magnitude of a squared times the magnitude of b squared times sine squared, and that's what you see here. Well, remember from trigonometry, the Pythagorean identity, which says that sine squared theta plus cosine squared theta is equal to 1. So sine squared, if I subtract cosine squared theta from both sides, you did this a lot when you did some proving some trig identities. So sine squared is going to be equal to 1 minus cosine squared, and that's what you see here. Sine squared has been replaced with this. All right, then what they did is they distributed this a squared b squared, magnitude of a squared times the magnitude of b squared, to each of these two terms. So this first went times this and then times this. So this times this, of course, just gives you the magnitude of a squared times the magnitude of b squared. And then we have minus, and then we're just going to have this times cosine squared, and that's what you can see here. Okay, so the next step is to go back to this formula that we had up here at the top, all right, that said that the magnitude of v times the magnitude of w times cosine theta is the dot product. Well, notice what this is. This is the magnitude of a vector squared times the magnitude of another vector squared equals the cosine of the angle between them squared. In other words, it's this squared. So if I take this side and square it, so I have the magnitude of v squared times the magnitude of w squared times cosine squared theta, then that means that will just be equal to the square of the dot product. And that's what you see here. Okay, it's just a and b instead of v and w. So it's the square of the dot product. All right, then what they did is they actually went to the component form. So they didn't say this, but we are taking a, vector a, to be a sub 1, a sub 2, a sub 3, and vector b to be b sub 1, b sub 2, b sub 3. And so that means that the magnitude of a, so the magnitude of a will be the square root of a sub 1 squared plus a sub 2 squared plus a sub 3 squared. We've seen this before. But now in this problem, it's not just the magnitude of a, it's the magnitude of a squared. So if I square both sides, then what I end up with is that the magnitude of a squared, of course, is just equal to a sub 1 squared plus a sub 2 squared plus a sub 3 squared. All right, so that's where this comes from. So that's the magnitude of a squared. Likewise, this is the magnitude of b squared, just b sub 1 squared plus b sub 2 squared plus b sub 3 squared. And then the dot product, of course, is just multiplying across. So a sub 1, b sub 1, a sub 2, b sub 2, a sub 3, b sub 3, and then we're going to square that. Now, here's where we leave out a whole bunch of algebra because it's just messy. So we're taking a trinomial times a trinomial, and then we're squaring another trinomial, and then we're subtracting them. So it's just a bunch of algebra. You have to be really careful about subscripts, blah, blah, blah. This is what you end up with when you're done. Okay, so just take my word for it. It's just a bunch of algebra, expanding, combining, refactoring. Okay, so what is this? Well, notice that this looks really familiar. Well, that's right here, isn't it? A sub 2 b sub 3 minus a sub 3 b sub 2 squared, and that's what we have here, plus a sub 3 b sub 1 minus a sub 1 b sub 3 squared, and then this matches this. But this is the square root up here, and this one's not. So again, if I square both sides of this, then I'll just get what's under here, which is what we have right here, and then I'll have the magnitude of a cross b squared, and that's what you see here. So this matches this. Okay, so that, remember, that's what we were trying to show. We were trying to show that this squared would give us this squared. So now that we have that, now that we have that this, I can rewrite this down here, the magnitude of a squared times the magnitude of b squared times sine squared theta. If I just take the square root of both sides of that, then over here I just get the magnitude of a cross b, and then over here I just get the square root of that is just going to be magnitude of A times magnitude of B times the sine of theta. Okay, and this piece right here, they're just kind of saying that we don't have to consider a negative here. First of all, magnitude is always positive. And remember that if we're talking about the angle between two vectors, then we're talking about an angle that's between 0 and 180. Okay, so somewhere in there. And the sine of every angle between 0 and 180 is positive. So this will always be positive. This is positive, this is positive. Sine of theta will be positive because sine is always between, or theta is always between 0 and 180, okay? Because we're dealing with, well, it could be equal to also, I think. But we're dealing with angles between 0 and 180. Okay, so there is the proof. I'm going to stop there and then we'll do one little